Magnetic flux density. We have already seen that we can represent the magnetic field by lines. The magnetic field lines always start at the North Pole and end at the South Pole. These lines are also known as lines of magnetic flux. Pay attention in the diagram. The magnetic field is strong where the field lines are close together, so a magnetic field is stronger at the poles of a magnet. We can say that the density of a magnetic flux is stronger at the poles, so the more field lines, the stronger the magnetic field. If we put another magnet next to the first one in this new picture, the magnetic field will be much stronger into this region. B is magnetic flux density, magnetic field strength. The flux density is measured in Tesla. Magnetic field associated with a current. An electric current in a conducting wire produces a magnetic field around the wire. The magnetic field produced by an electric current is represented by magnetic field lines go around the wire, and the direction is always oriented perpendicular to the direction of the current flow. Look at the diagram. The right-hand grip rule will help you to find the direction of magnetic field. Put the thumb of your right hand along a wire in the direction of the current. Now your fingers point in the direction of the magnetic field. Look at the diagram. If the current direction is reversed, the direction of the magnetic field is reversed. Pay attention. If we place a wire that carries a current in the presence of a permanent magnet, it will occur interaction between the two magnetic fields, causing a force that pushes the wire at right angles. This is called the motor effect. Pay attention now. Magnetic field, wire, force acting on the wire. There is no motor effect force if the current and magnetic field are parallel to each other. To predict the direction in which a straight conductor moves in a magnetic field, you can use left-hand rule. Spread out the first two fingers and the thumb of your left hand so that they are at right angles to each other. Let your first finger point along the direction of the magnetic field and your second finger point in the direction of the current. Your thumb then points in the direction in which the wire moves. To calculate the force on a wire carrying a current at right angles to a magnetic field, use the equation F equals Bell. Force in newtons, magnetic flux density in Tesla, current in amps, length in meters. Let's see how it works. Example. A current of 3 amps flows through a 50 centimeters wire. Calculate the force acting on the wire when it is placed at right angles in a 0.5 Tesla magnetic field. Take the values given in the question and substitute into the formula. Electric motors. A coil of wire carrying a current in a magnetic field experiences a force that tends to make it rotate. This effect can be used to make an electric motor. Figure below shows a coil of wire that is able to rotate about an axle. Starting from the position shown in the diagram, current in the left-hand part of the coil causes a downward force, and current in the right-hand part of the coil causes an upward force. The coil rotates anticlockwise because of the force described above. When the coil is vertical, it moves parallel to the magnetic field, producing no resultant force. This would tend to make the motor come to stop, but two features allow the coil to keep rotating. When the coil is at the vertical position, the coil keeps turning due to inertia. A split ring commutator changes the current direction. Current in the coils is reversed. The magnetic forces acting on the coil is reversed too. Current flows in the opposite direction through the wire in the coil, and each side of the coil is now near the opposite magnetic pole. This means that the motor effect forces continue to cause anticlockwise rotating of the coil.